Good evening, students. I hope you are doing well. Just a few minutes. We'll be waiting for other participants. If not, we'll be continuing in 2-3 minutes. Welcome, Varda, JNV Varda. So, can hear me clearly and can you see my video and presentation clearly? Do respond in the chat. Tell me whether my audio and presentation is clear or not. JNV Varda, can you hear me? Others, can you hear me? Yeah, okay. Let's start then. No. Before this, we were discussing all the gas laws, right? Right. I hope you remember everything. No. Let's have a small recap about what we discussed in the previous sections, right? So first thing, we need to know what is a gas, right? Where they are far away from each other and intermolecular interactions are very much less when compared with the liquids and solids. Now, then next we came to Boyle's law, Charles' law, and Gay-Lussac's law and Avogadro's law based on 4 parameters. What were those parameters of gases we were considering to derive these laws? The 4 parameters were pressure, volume, number of moles, and temperature. Now, what we'll be doing, we'll be taking these 4 parameters, measurable parameters of a gas, and what we'll do, we'll keep any of the 2 variables on this constant, and we'll be relating with the other 2 constants. Right. This is what we'll be doing. Now, in Boyle's law, what are the constant variables we'll be taking here? What are the constants we'll be considering here? Can anyone answer that? What are the constant terms in Boyle's law among pressure, volume, number of moles, and temperature? You can answer in the chat. Yeah. Uh, Boyle's law, what are constants? Number of moles of gas is constant, right? We'll be taking a particular container, and what we'll be doing, we'll keeping a piston above it, and we'll be changing the pressure on the gas and how it will affect the volume of the gas. This we will be seeing, right? Now, in this, if uh, number of moles is constant and temperature is constant, what we'll be relating with pressure and volume. The other 2 variables are what? Pressure and volume. How they are related? Pressure is inversely proportional to volume. If I'm increasing the pressure on this, what happens? The volume of the gas will be decreasing. If I'm decreasing the pressure, that means the piston will go above. At that time, what happens? The volume of the gas will increase. That's what we have seen. Now, in Charles' law, what are the constants? The constants are number of moles again and pressure. Now, what is the relation here? Volume is directly proportional to temperature. As we increase the volume, what happens in the, let's say we have taken a container. Now, the same container we are taking. Now, if you are heating this, what happens? Due to the to keep the pressure constant, what happens? The piston will go above and the pressure will be constant and volume will be increasing due to increase in kinetic energy. Then what we have seen, what are the constant variables in Gillisak's law? That is number of moles and what? Number of moles and volume are the constants. And by keeping these two variable constants, what will be relating with pressure and temperature? Here we have seen pressure is also directly proportional to temperature. If you are increasing temperature in the same container again, if you are increasing the temperature. Now I'm saying the piston is constant. Then what will happen? Then what will happen? The volume of the gas will no, if you are sorry, if we keep the volume of the gas constant, what happens? The collisions will increase towards the surface as the volume is constant. If the collisions are increasing, the pressure of the gas will also increase. Now, come to Avogadro's law. What are the constant terms here? Nothing but pressure and temperature. If pressure and temperature are constants, then we'll be relating with what variables? We'll be relating with volume and number of moles. Volume is also directly proportional to number of moles. How are we saying that? Now, in Avogadro's law, we'll be considering what conditions? STP conditions, right? Do you remember? What are the STP conditions? At 0 degrees centigrade, that is 273 Kelvin, and 1 atmosphere pressure, 1 mole of any gas will be occupying, that is 1 mole of gas will be consisting how many Avogadro number of molecules? How many molecules? Avogadro number of molecules, right? What are those? 6.023 into 10 power 23 molecules, right? Now, at STP at 0 degrees centigrade and 1 atmosphere pressure, 1 mole of any gas will be occupying exactly how much volume? 22.4 liters of volume. If you increase the temperature, what happens to volume? Volume will be increasing. Now, according to Avogadro's law, what is it saying? As we increase the number of moles also, the volume of the gas will also be increasing. Now, we used all these 4 laws and what we derived? The ideal gas equation, that is PV is equal to nRT. Now, we also derived a relation between molecular mass and gas densities. What are those? Now, what is molecular mass? Nothing but what is the mass of Avogadro number of molecules of a particular atom, maybe molecule, right? Now, if you want to relate between molecular mass and densities, we'll be using ideal gas equation itself, that is PV is equal to nRT. If we elaborate the number of moles, nothing but what is number of moles equal to? Weight by molecular weight, right? Nothing but into RT. The same thing will be there. Just we elaborated the number of moles weight by molecular weight or mass by molecular mass. Same thing. No, it is not like physics. If we say mass or weight, many things will change right in physics. But here we'll be saying the same thing itself, nothing more. No, we'll be rearranging to get the density value here. How we'll be arranging is that weight by volume is equal to, just I'm sending the volume term toward the other side and pressure term towards the other side. Pressure into molecular weight divided by RT. Just I am rearranging the formula. Now, what is weight by volume? Nothing but density D is equal to P into molecular weight, capital M, I am representing with, divided by RT. This is a new relation between density and ideal gas equation, where D is equal to, density is equal to Pm by RT. What is P? Pressure. What is M? Molecular weight of the gas, whatever you are taking. And R is gas constant, T is temperature. And remember one thing, whenever you are taking temperature, take it in Kelvin only. When you are doing the calculations, take it in Kelvin only. Now this is about the previous class, and let's move. Just a small recall test. Now, if you know what the curves we were discussed in the previous case, in each case, Boyle's law, Charles law and all, which curve shows Charles law? I'll be giving the poll in a minute. Try to see the question. In a minute, I'll be launching the poll. Oh, sorry, the poll is not working. You can text the answer in the chat. I'll be seeing that. Just write, no issues. It may be right or wrong. Try. Which curve shows Charles law? You know, right? What happens? What is Charles law? Nothing but at constant pressure and at constant pressure, given number of moles of gas will be having volume is directly proportional to temperature. That's what we have seen. No. Let's see. What did Charles law say? Volume is directly proportional to temperature. That is, y is proportional to x graph. What is y is proportional to x graph? Nothing but a straight line, right? But let's see, in the first case, it is V versus T, nothing but Y versus X, right? Like this graph. Now it is a straight line, increasing slope. No, it is wrong, right? This is not the graph. Now next is X is equal to 1 by T and Y is equal to V. We need to rearrange this form. V is proportional to T in Y is inversely proportional to X form. How we can do that? V is proportional to 2 is there. Now I can write V is proportional to 1 by 1 by T. Can I write like this? This is same thing, right? V is proportional to T itself. Now, if you want to write it, nothing but Y is inversely proportional to X graph. Now, remember PV graph? PV is inversely proportional to V graph. What is that graph? Rectangular hyperbola. This is also same thing, the rectangular hyperbola. So second option is the correct option. Now you can verify C and D also. If you have any doubts, you can clarify it. Try them at as your homework, whether C and D graphs are correct or not. Now, today we'll be discussing about Dalton's law of partial pressure and then Gram's law, and if type permits, we'll be going to kinetic gas equation or kinetic gas theory. Okay. Now, firstly, what happens in Dalton's law of partial pressure? Now, how many of you had balloons or blown balloons? Did you blow balloons? Text in the chat. Did you blow the balloons anytime? Never blown balloons or what? Fine. Ah, okay, fine. Leave the example. Now, what does Dalton's law of partial pressure say? At constant temperature, for a mixture of non-reacting gases, remember, non-reacting gases, the pressure of gases mixture is equal to sum of partial pressure of component gases. How is he saying that? Now, let's say we have a wall. We have a wall. Now, there is molecule A here, right? What happens? This molecule has a probability of colliding with this wall, gas molecule. Yes, right. It will not be staying at that particular position itself. If it is colliding with this molecule wall, it will be showing a certain force on the wall. Now, here, due to that force, we'll be seeing a pressure due to molecule A. Now, let's say there is molecule B in another container. Now, it is also colliding with the wall. This will also show a certain pressure according to B atom itself. Now, if I take A individually, let's say this is the A cylinder and this is the B cylinder and this is the C cylinder. Three types of gases I'm taking. So three types of molecules will be hitting the wall differently. They'll be not hitting the same way if they are different gases. Now, each gas is showing different pressure. Let's say I'm combining all these three into a single vessel, that is A, B, C gas are in single container itself. Now what will happen? A is hitting with its force, B is also hitting with its force, and C is also hitting with its force. And C is also hitting with its force. Now if I want to calculate the total pressure on the wall, at a time these three are hitting. That means the pressure will be P of A plus P of B plus P of C. Partial pressure of A. Why we are saying partial pressure? Nothing but we are taking the total mixture in this ABC mixture. A is showing a small part of the total pressure. That's why we are saying partial pressure due to gas A, partial pressure due to gas B, partial pressure due to gas C. That is what the law is saying. That is at constant temperature, if we take, and if we take non-reacting gases in the cylinder. Why we need to take non-reacting gases? If we take reacting gases, let's say nitrogen and hydrogen are there, and we are providing good temperatures and all, so that they will be reacting. Then what happens? It will give rise to ammonium gas. That is new gas, right? Those gases are totally changing into another gas, so that the pressure will totally be different, and it will not be equal to the pressure of nitrogen and pressure of hydrogen gas here. So that's the main reason we should see that the gases are not reacting with each other and giving rise to new products. The gases should be inert to each other. They shouldn't react with each other. Okay. Now at that point only, the total pressure will be equal to pressure of each individual gas. And so on, if there are n number of gases, Pn. Okay. Now, in the same way, if let's say I'm taking 1 mole of gas in A cylinder and 2 moles of gas in B cylinder uh, and another 2 moles of gas in C cylinder. Now, what are the total number of moles present in the ABC gas cylinder? I'm saying 1 mole of gas is present in cylinder A, 2 moles of gas is present in cylinder B, 2 moles of gas is present in cylinder C. Now, what is the total number of moles present in the last cylinder, ABC cylinder? Can answer in the chat. Yeah, where the total number of moles is again equal to how many moles of each gas is present, right? Nothing but 1 mole plus 2 mole plus 2 mole, that is equal to how much? 5 moles. 5 moles of gas is present in this particular cylinder. Na plus Nb plus Nc, so on to n number of moles of molecules. That is what we need to see. Clear everyone with the Dalton's law of partial pressure? If you have any doubts, you can raise your hand. If you're clear, I'll be moving to the next slide. No. All of you know, have you ever blown air into the water? I hope you did. Or did you take a soap bubble and blow air into it? I think you have done these things, right? What happens here? Generally, whenever we blow air inside the water, what happens? The air bubble will come and will come outside. But let's say we are collecting these bubbles. Let's say this is the setup and this is the water. And now I'm keeping a straw inside like this. And from here, I'm blowing the air. Now what I'm doing, I'm collecting these bubbles in a U-shaped tube, keeping upright. Now these bubbles will be collected in the gas, right? Collected in the test tube. Now what happens? These bubbles not only consist the gas, but also some moisture inside the gas, right? This will be happening. Now this is nothing but a concept which we need to apply for the problems here. Whenever they give you aqueous tension or something like that, how to apply it. It has been observed that gas are generally collected over water and therefore are moist. Whatever gas are collected here will be having some part of water content, some moisture content actually. Then whatever pressure it is showing on the water surface is different. It is not only due to the pressure of gas, right? As I said, if you are taking two gases, the pressure will be due to two gases, not only one gas, right? Now, same concept we need to apply here. The pressure of moist gas, the pressure of moist gas is equal to, now let's say the gas is dry. The pressure of dry gas plus the pressure of water, right? Whatever water vapor is there or moisture is there in the gas, pressure due to that moisture as well as pressure due to dry gas. Both if we mix, that will give the pressure of moist gas. Now, if you want to find out the pressure of dry gas, what it will be equal to? Nothing but pressure of moist gas minus pressure of water. Now, this pressure of water, we will be calling it as aqueous tension. Aqueous tension. Okay. Just remember, whenever they give you aqueous tension or something, just try to see whether they are asking the moist gas pressure or dry gas pressure. Based on that, you need to see. If they are asking moist gas pressure, pressure of gas plus pressure of water. They are asking only dry gas. That means you need to remove the moisture pressure from the moist gas. Clear, everyone? Moist gas minus aqueous tension. Aqueous tension. Simple concept, nothing more. If you have any doubts, you can text in the chat here. If you are clear, the whole concept here is nothing but first thing, how many gases are there? The pressure will be due to all the non-reacting gases. Now, if pressure of gas A is A, PA, pressure of gas B is PB, you need to add PA plus PB to give the total pressure. The same thing we are doing in the moist gas also. Now, in moist gas, what are present? Along with gas particles, there are water particles also. The pressure due to water particle as well as pressure due to gas particle. If you combine both of them, you'll get the pressure of moist gas. Simple. Now, if you understood the concept, try to answer this. Which mixture of gases at room temperature does not obey Dalton's law of partial pressure? What you need to see here, whether the gases will react with each other or not. Try to see. I'll give you a minute and text the answer in the group, sorry, in the chat. Okay. What we need to see here, whether the gases are reacting with each other or not. If the gases are reacting, can you apply Dalton's law? No. The gases should not react with each other. NO2 and O2 at normal conditions, they will not be reacting. So fine. Here we can apply the Dalton's law. Next, NH3 and HCl, right? What are these? Base and acids. Will they react? No, these gases will react immediately to give rise to what? NH3 will react with HCl and give rise to NH4 plus and Cl minus, where a dative bond is formed between nitrogen and hydrogen, right? If the gases are reacting, can you apply Dalton's law? No, you cannot apply because the partial pressures are changing here. The molecules are, number of moles of molecules are totally changing here. We cannot apply Dalton's law here. Now let's see C option C also. CO and CO2, carbon monoxide and carbon dioxide, that will also not react. SO2 and SO3, those also will not be reacting at normal conditions. Now, next. As you know, B is the answer. Do you have any questions in Dalton's law of partial pressure? Now, one more concept test, that is the partial pressure of hydrogen in a flask containing 2 grams of hydrogen and 32 grams of SO2 is. He is asking partial pressure of hydrogen. What are given? First write down whenever a question is given. First write down what is given. Try to note in your notes what is given. I'll give you a minute and then I'll be solving the question. Let's continue. Now here what is given? Weight of H2 is given. Weight of H2 gas is given, that is 2 grams. Next, weight of SO2 is given, that is how much? 32 grams. Now, first thing, convert the weight into number of moles. NH2 is equal to 2 grams given, right? 2 by how much? 2. Molecular weight of hydrogen is 2. Nothing but number of moles of hydrogen is 1 mole. And number of moles of SO2. What is the weight of SO2 given? That is 32 grams. And molecular weight of SO2 is molecular weight of SO2 is nothing but from sulfur 32 grams molecular weight plus from oxygen 2 oxygen atoms are there, 2 into 16, that is 32. Total how much? 64 grams. Ones are, twos are, that gives us half mole of sulfur dioxide. Clear. Now we have known the what is the number of moles present, right? Now here, how to find out the partial pressure of hydrogen when you don't know partial pressure of any gas or the total pressure? Then we need to relate between the partial pressure and total pressure. How to do that? Now, partial pressure of gas 1, let's say gas H2. H2 gas is equal to, what is it equal to? Volume is constant, right? Both are in same cylinder into number of moles of H2 into RT. Now, what is total pressure? Nothing but P total is equal to total moles into RT, total volume V. Now, how to relate between these two? Just take a ratio of PH2 by P total. V by V is there. Both will be cancelled out. And then NH2 by N total into RT by RT. Both will be cancelled out. Now, at last, what are we left with? Pressure of H2 gas by total pressure is equal to number of moles of H2 gas by total number of moles. What is total number of moles here? Nothing but moles of hydrogen gas plus number of moles of sulfur dioxide gas, right? Now substitute that. Pressure of H2 is equal to total pressure into moles of H2 gas by moles of total number of moles. Now you can elaborate the total number of moles, nothing but moles of H2 gas by plus moles of SO2 gas. Now, what are you observing here? Number of moles of one gas by total number of moles. What is that? Nothing but mole fraction. Clear, everyone? This is nothing but mole fraction. N H2 by total number of moles, that is moles of H2 plus moles of SO2 is equal to mole fraction of H2. You can directly substitute that also, your wish. Now, as we know, number of moles of H2, that is 1 mole divided by total number of moles, that is 1 plus 1 by 2. Pressure of hydrogen is equal to how much? Nothing but if you do the LCM here, that will be 3 by 2. So it will go around, do the calculation, 1 by 3 by 2 into total pressure. The answer will be what? Pressure of H2 is equal to 2 by 3 total pressure, 2 by 3 times of total pressure. That will be your answer. Clear everyone with this problem? Are you clear? If you have any doubts, you can text in the group. Sorry, text in the chat. Simple. What you need to see, first find out the number of moles and do the mole fraction of whatever gas is asking. And what is the main equation you need to remember here? You need to remember is pressure of any gas, let's any pressure of first gas is equal to mole fraction of that gas into total pressure. That gives you the answer. Simple. Do that thing. Okay. Now moving on to next concept, that is Gram's law of diffusion. What is Gram's law of diffusion? Can you see the picture here, all of you? If you can see the picture, you can text in the group. What is happening there? What is happening? The gas is being diffused. The smoke is being diffused, right? Diffusion is nothing but a spontaneous intermixing of two or more gases to form a homogeneous mixture. Now let's say you have taken a scent bottle and broken it in the middle of the class. What will happen? You broken it in the middle of. Now will the scent go in any single direction? No, right? The scent will spread across the room along the same velocities, right? Nothing but diffusion is a multi-directional process. Multi-directional process. Now we cannot say that diffusion will occur only through your door, only through your window, and it will not go through any other possible open spaces. You cannot say like that. It will go through all the directions, all possible ways. We cannot say it will go only through one direction because we are not restricting anything here. There will be a large area, open area, so that it can diffuse easily. No. One more concept we need to see, that is effusion. Effusion is also a diffusion process, but when we'll be calling a diffusion as effusion? Only when the diffusion is occurring, only when diffusion is occurring through a tiny hole due to pressure difference. This is called as effusion. Clear? Now we can see in this GIF, right, where there is only small hole here. Where there is only small hole here and there is a small hole here. Now, through that hole itself, the gas should diffuse. Is there any other possibility? No, right? So that's the main thing, as it should diffuse through only that particular small area. And due to the pressure difference, the diffusion is happening very rapidly. This will be calling it as effusion process. Clear? Understood the difference between diffusion and effusion? Diffusion is multidirectional and effusion is occurring through only a small area and it is unidirectional in nature. Unidirectional. Clear with it? Now next, according to Gram's law of diffusion, what does it say? Now we'll be seeing the actual law. What does Gram's law of diffusion say? At constant temperature and pressure, the rate of a gas, the rate of diffusion of a gas or effusion of a gas is inversely proportional to the square root of molecular weight or square root of vapor density or square root of density of a gas. That's what he's saying according to Gram's law. Now what we can see here is, let's say you have a 500 kilograms friend, a big fat friend, and one is 50 kilograms friend. Now tell me who can run faster in a normal condition, let's say. Right. The 50 kilogram student, like your friend, can run faster when compared to the 500 kilogram. Yes or no? Right. The same thing with the molecules also. If the heavier the molecule, the rate, the movement will be slow. If the lighter the molecule, the movement will be fast, right? Now the same thing here, what he did, rate of diffusion is inversely proportional to square root of molecular weight, he said. Now what is vapor density? Do you know? Uh, Vapor density is nothing but if you are taking the density of any particular gas relative to the any other gas, that is called as vapor density, relative density or vapor density. If you are taking the comparison between molecular weight of one gas with hydrogen gas, molecular weight of hydrogen gas, it is called vapor density, where vapor density is equal to molecular weight of gas, molecular weight of gas by molecular weight of H2 gas. This is nothing but vapor density. Now what is molecular weight of hydrogen gas? 2, right? So molecular weight of gas, M gas I'm writing, by 2 is equal to vapor density. Molecular weight of gas is equal to 2 into vapor density. Just substitute that in the same relation, that is rate is inversely proportional to molecular weight, square root of molecular weight. You'll get the same value, that is inversely proportional to square root of vapor density. Let's see how is that. Rate is inversely proportional to molecular weight, right? So if I write relation R1 by R2 is equal to under root M2 by M1, right? Now substitute the vapor density values, that is 2 VD2 by 2 VD1. Both 2's will be cancelled, and what is the relation you'll be getting at last? VD2 by VD1. That is inversely proportional to root of vapor density. The density also same thing, where we have derived the equation, right? Where density is equal to Pm by RT, where if pressure and temperature also constant, nothing but molecular weight of gas is directly proportional to density of the gas. In that way, you can see again, rate is inversely proportional to under root density. Clear everyone with these relations? The three relations you need to remember in this case for now. Okay. Are you clear, students? No. If you are clear, we'll move to next slide. Just try to understand the concept and apply it here. First, write what is given in the question. The densities of hydrogen and oxygen are given as 0 point density. Density of hydrogen is given as 0.09 liter inverse, and density of oxygen gas is given as 1.44 liter inverse, right? Now he is asking rate of diffusion of hydrogen is given, that is RH2 is given as 1. Rate of diffusion is represented with small r. Rate of oxygen in the same units. He's asking rate of oxygen. Now, do you remember what is the relation between rate and density? Is it inversely proportional to square root of density or directly proportional to square root of density? Can answer in the chat. It is inversely proportional to square root of density. Rate is inversely proportional to square root of density. Now apply that here. R1, that is RH2 by RO2 is equal to under root DO2 by DH2. Substitute the values where RH2 is given as 1, right? 1 by RO2 is equal to density of O2 is given as 1.44 by density of hydrogen is given as 0.09. Just rearrange it properly. Just RO2 is equal to under root 9 by 144. This is nothing but 9 ones are 9 16s are. Here RO2 is equal to under root 1 by 16. That is nothing but 1 by 4. What is the rate of oxygen? Nothing but 1 by 4. Clear everyone how to find out? Just see the relations, what is given data and what you need to relate. Do you have any questions in this problem? Okay. If you don't have, let's move. Now, before going to rate of diffusion in terms of volume, we have one more relation. Let's say if pressure is variable. Let's say if pressure is variable. If pressure is variable and temperature, number of moles, these are constant. Now, what happens? Temperature and volume are constant. Then what happens to rate of diffusion? Now, first thing we know that is rate is inversely proportional to root of molecular weight. Now, as the pressure inside a container increases, what happens to effusion? This is a small hole. What happens? The effusion or diffusion will increase. I'm increasing the external pressure rate. Nothing but rate is directly proportional to pressure by under root m. Clear, everyone? There is one more condition there. If I take R1 by R2 is equal to rate of first gas by rate of second gas, pressure of first gas by pressure of second gas under root m2 by m1. This is when we are taking two gases and both have different pressure and different molecular weights, then how to relate. This is the case. Clear, everyone, with this? No. Now, if that's the case, next we'll be moving to how to find out rate in terms of volume. Can we do that? Yeah, we can do that, right? Now, volume means he's asking rate in terms of volume. Now, this is the container and this is the piston above it and there is a wall gas present here. Now, the effusion is occurring through this particular hole, let's say. Now, what we need to see is that how much volume of gas is escaping through this particular hole at unit time. What we need to see, rate is nothing but here, rate is equal to volume of gas escaped, volume of gas escaped by time taken for the total volume of that gas to escape. If you, let's say 2 liters of gas is escaping from a 10 liters. Now, how much time it is taking for this 2 liters of gas to escape? That is nothing but time taken, and that gives us the rate. Volume of gas escaped by time taken. Nothing but V by T. Rate is proportional to V by, if you write in the ratio R1 by R2, that is nothing but V1 by T1 by V2 by T2. Let's say we have two gases in the same container itself. One is blue gas, one is red gas. Then what we need to see is, as we keep the hole open for the same time. Now the time is same. So at last we can write if time taken is same, if time taken is same, then what we can write it as R1 by R2 is equal to V1 by V2. Clear, everyone? This is one more relation between rate and volume of gas escaped, not volume of gas escaped. Clear with this, everyone? Any doubts? I hope you're clear. And if you move to the next topic, that is rate of diffusion in terms of number of moles of gas escaped. The same thing, if you keep the time constant and if you see how many moles of gas is being escaped for that specific time of two gases. Here also same thing, how many gas rate is equal to, sorry, not able to write, one second. Let me, now I can write. If we want to write rate in terms of number of moles, rate is equal to number of moles of gas, number of, sorry for this, rate is equal to number of moles of gas escaped. Don't forget the number of moles of gas escaped by, now for this gas to escape, for let's say 2 moles of gas escaping, for that 2 moles, how much time is taking? By time taken. That gives us the rate, nothing but N by T. If we do it as R1 by R2, that is equal to N1 by T1 by N2 by T2. If the time taken is same, the both gas in the same cylinder, and if you are opening the uh, hole for the same time, then the time taken will be same. If time taken is same, if T is same, rate of first gas by rate of second gas is directly proportional to N1 by N2. How many moles of gas is present in the cylinder? Okay. Now, if we write the rate according to in terms of rate in terms of distance. What is this distance? This is a very important concept. Rate in terms of distance. Okay. If you have noted this, I'll be erasing it. Okay. Quickly note it. The rate in terms of number of moles. Okay, fine. If that is done, let's continue. Rate in terms of distance. Rate in terms of distance. No, the same thing. Remember how a 500 kilograms person can run and 50 kilograms person run. No, in the same way, gas also move in different velocities. Now, let's say one gas is moving fast, that rate will be more. If the gas is moving slow, the rate will be less. Now, if you see in the same way, we are taking the same cylinder again, and there is open hole here, and there are two types of gases. Let's say gas A is moving as well as gas B is moving. Both can move with different velocities. If the velocity is more, that means the distance covered by the gas also is more, right? In the same way here, rate is nothing but from the hole how much distance it is moving. This is L. If this is X, how much distance it is moving, how much distance the gas is moving. Rate is nothing but in terms of distance traveled by the gas, distance traveled by gas by time taken, how much time it is taking to cover that distance by time taken. That is nothing but rate in terms of distance. Now, how does questions come in this case? In terms of distance, what they'll be doing is they'll be giving a cylinder like this, and they'll be saying that there are two holes on the left and right side. And they'll be saying gas A is coming from left and gas A B is coming from right. Now, if this point 1 is the center, point 1 is the center, and this is point 2, and this is point 3. Okay, you can see that, right? Point 1, point 2, and point 3. Now tell me if rate of A or velocity of A gas is more. Velocity of A is greater than B. Then at which point will the gases meet? At point 1 or point 2 or point 3? You can enter the values in the chat, whether they'll meet at position 1, 2, or 3. If velocity of A is more and velocity of B is less, where the gases will meet at point 1, 2, or 3. Yeah, the gases will meet at point 3. Why? Because as velocity of A is more, it will cover more distance, and velocity of B is less, so it will cover less distance. Now, if you see exactly after middle point, that is 1, what is the point present? 3, right? Towards B side, which is moving slower. So that's why at point 3, the gases will meet. A and B will meet. So in this way, they'll be asking the questions, or sometimes they may give the distance and find out X or L. In that way, they'll be asking. No. What are the applications of Gram's law? Where do we use this? Actually, is it used anywhere? Yeah, we do use to separate isotopes. What are isotopes? Where the molecules are same, but due to their mass number will be different here. If you see in hydrogen, deuterium, and tritium cases, right? What happens? Their neutron number is different. So in that way, we'll be using this Gram's law to differentiate between different types of gases based on molecular weight. Because based on molecular weight, again, the velocity of the gases change. Due to that, rate of the gases change, so that we can separate the gases. Now, this process is called as atmolysis. See here, you can note this down. Isotopes are separated using this Gram's law, as well as for a gaseous mixture, component gases can be separated. This process is known as atmolysis. Clear, everyone? This is about Gram's law. Still, we need to speak some concepts here. But did you get it? Applications are there, few applications. Class, did you get the concept properly? Yeah, good to know. Now, if we move on, next is kinetic theory of gases. Right. Now, before that, let's summarize what we learned in Gram's law of diffusion. Now, R1 by R2, if you write, first relation is between molecular weight, nothing but M2 by M1. Now, next we related with vapor density, that is VD2 by VD1. Next related with density, that is D2 by D1. Rate is inversely proportional to density, inversely proportional to vapor density, inversely proportional to molecular weight under square root. Don't forget that. Next, afterwards we related with the pressure, where pressure was variable for two gases. Then what we did, as pressure increases, rate of diffusion increases, P1 by P2 under root into M2 by M1. This was we derived. Now, after this, we tried to make a rate in terms of volume of gas escaped, right? V1 by V2. This we have seen. Next to what we have seen in terms of number of moles, N1 by N2. In terms of distance, we have seen L1 by L2. L1 by L2. We can represent in that. L1 by L2. These are all the rate equations we have seen. So try to interrelate between these. If you ask given molecular weight and is asking volume, you can relate it in this way directly using rate equations, not the kinetic rate equations. I'm saying Gram's law of rate of diffusion equations. Clear? Now let's move to kinetic theory of gases. Now, this is a very much important concept, and remember this theory in a simple way. Now, firstly, what you are taking a container, and you are taking a you are taking a container. Now, in this container, let's say there are different molecules, right? These are nothing but molecules are, these particles are nothing but molecules are atoms. That's the first postulate of kinetic gas theory. Clear? Now, these molecules, what happens? Let's say you are taking nitrogen gas in the container. Now, each nitrogen molecule will be having same property or different property, right? As they are same atoms with same properties, right? They'll be having same chemical and physical properties also, as all of them are same atoms. That's the second postulate. Now, if you see the third postulate, molecules are constantly in random motion along straight lines. What is saying that each molecule will be moving here and there, and that will be moving in straight line, not in form of a wave or anything like that. Or they'll not be taking a parabolic path due to gravity. Why? Because we'll be in case of ideal gas situation, what we'll be considering it as the gas particles are a minute point masses. We'll be considering the gas particles as point masses. That's the only reason why gravity is not acting on them. If you take a heavier mass, definitely gravity will ask, right? But in gases, as they are very light particles and they don't have interactions between each other, no much interactions, let's say. Due to that, we'll not be seeing the parabolic path or something like that. Here we'll be seeing gases molecules will be seeing a straight line, right? If the gases are affected by gravity, then can you be in this atmosphere like this? No, right? Every gas is coming down. There is some pressure due to that. That is atmospheric pressure, right? That's a different case. Now, third point, fourth point, all the collision of gas molecules among themselves and with the walls of the container. Now, this molecule can collide with this molecule, and this molecule can collide with another molecule. This all happens. Let's say this is also colliding with the walls of the container. Now, due to these collisions, the energy is not transferred between them, or the momentum of the particle is not transferred towards the wall or with the other molecule here. These collisions are called as elastic collisions, where momentum is conserved, it is not changed. Velocity is also same, it doesn't change. Clear, everyone? These are nothing but elastic collisions. Now, if you go to the next slide, the fifth postulate, the pressure of gas is due to collision molecules with walls of the container, right? What is happening? If it is the wall, this is the wall, and the molecule is going and colliding. It will have a certain velocity, so that it will be having a probability of colliding with the wall. If it is colliding, nothing but force is acting on a particular area. Now, force on particular area is nothing but pressure. Yes or no? Right. That is what we have seen. Due to these collisions only, pressure will be calculated. As collisions are increasing, pressure will be increased. What happens as we increase temperature? First thing, thermal energy of the molecule increases, because of which kinetic energy of the molecule increases. And if kinetic energy is increasing, velocity of the molecule increases and collisions will increase, due to which indirectly pressure will increase. Now, sixth postulate, that is kinetic energy of a gas depends only and only on absolute temperature, right? Why? As we increase the temperature, thermal energy of the molecule increases and kinetic energy will be increased as velocity will be increasing. The volume of gas occupied by gas molecules is negligible when compared with volume of gas. What does that mean? Now, whenever we take an ideal gas in a container, now what did I say? They are considered as point masses, right? This is the gas particle dispersed in the container. Now, what is the volume of the container? Let's say V is the volume of container. Now, let's say I arranged these gas particles side by side each other, beside each other. What happens? They will be around in this way. Now, the volume of this gas particles, it's, let's say, V gas molecules. V gas molecules, and this is V container. Now, what is volume of gas? What we actually take is that how much empty space, volume of gas is nothing but how much empty space, how much empty space is available for the gas to move freely. Now, if you see this, how much empty space is available for the gas to move? Nothing but V container minus V gas, right? Yes or no? V gas molecules. Now, this is equal to V container minus V molecules, right? Now, if you see, this volume of the molecules is very small, that will be neglecting them. That is what the sentence is saying. The volume occupied by gas molecules is negligible when compared with the volume of gas, nothing but volume of container. If you see that the volume of molecules is very small, that much very small value, if let's say 100 is there and volume of gas molecule is 0.1. If you remove 0.1 from 100, what it is doesn't affect much, right? 99.9999. So it doesn't affect much. So that's the reason why we'll be neglecting the volume of gas molecules if you are taking gas molecules as point masses. Now, one more important is there is no intermolecular force of attraction among molecules. These all are postulates, not the reality here. There is no intermolecular force of attraction among molecules, right? That is one of the postulate. And due to this point masses, gravity is also neglected here. Clear, everyone? These are the postulates, and tomorrow we'll be seeing what is kinetic gas equation and how we derive it and all. What we'll be doing is that, firstly, I said, right, one thing is, just remember this story, you'll be remembering the total postulates of kinetic gas equation theory. First thing, what you'll be seeing, there is a molecule in the container, yes or no? There, if you have molecules in the container, all are same, they'll be having same properties. Now, each molecule also will be having a certain velocity, right? What happens? These molecules will be moving here and there. Due to that, what happens? Collisions will happen. Collisions with molecules as well as collisions with walls. Now, what we consider here is these collisions are elastic collisions. Clear or not? Now, after collisions, what will happen? Due to collisions, what is present? Due to this force on the wall, pressure will be present, right? Due to this, pressure will be acting. Now, what all things will be seeing? The molecule will moving in a straight line. It will not be affected by gravity, right? And we'll be considering the volume of the container as volume of gas itself, where we'll be neglecting volume of gas molecule because they are point masses. Okay, all the postulates you can remember by imagining the container itself. Okay. If you want to, I can continue one of the equation. Do you want me to continue, or let's continue the derivation completely in the next class? Just I'll give you the kinetic gas equation here, or the relation between PV and kinetic energy. PV is equal to 1 by 3 mn u RMS square. This is what we'll be deriving. Kinetic energy is equal to half mn u RMS square. N is nothing but number of molecules in the container. N is nothing but number of molecules. And URMS is nothing but root mean square velocity. Nothing but URMS is equal to root mean of velocity squares, u1 square plus u2 square. There will be a number of particles, so that un square divided by mean of the velocities, square velocities, under root is nothing but URMS. These all things will be deriving tomorrow. How we will be deriving pressure, how we will be deriving kinetic energy, and we can relate kinetic energy with pressure and volume terms. So if you have any doubts, you can clear it now, or else you can leave the meeting. What did we learn today? First thing is Dalton's law, right? Now after Dalton's law, what we discussed? Graham's law. Now after Graham's law, we discussed KTG postulates, nothing more postulates, right? Now in Dalton's law, what we discussed, the total pressure is nothing but a sum of pressure of all the individual gas pressures, nothing but partial pressure of each gas. Total pressure is equal to P1 plus P2 plus so on to Pn gas. How many gas molecules are there? So much. So on will be adding all the partial pressures of each gas. In Graham's law, what we discussed? Rate of diffusion or rate of effusion. This is what we learned today. Now, if you find, you can leave the class. Plus, if you have any doubts, try to clarify them. Okay, then. If you have no doubts, I'll be ending the meeting.